In August of 2020, a massive windstorm hit central Iowa. This storm, called a derecho, or an inland hurricane, caused billions in damages and led to several deaths. The driving force behind this storm, and the main cause of its destruction, was wind.
Wind is the result of several different factors, including the uneven heating of the surface of the Earth by the sun, the formation of the local landscape, and the rotation of the Earth. These different types of winds can cause several different weather phenomena, including blizzards, jet streams, tornadoes, hurricanes, and derechos, like the one mentioned above. Wind can also just be a gentle breeze on a sunny day.
We can describe how wind works with a variety of gas laws. These laws describe how gases behave mathematically. The first law, Boyle's law, is the relationship between volume and pressure. As volume goes down, pressure goes up. Think of it like a balloon. If we shrink the balloon, the air inside gets compressed together, meaning the pressure goes up.
The second law, Charles' law, describes the relationship between temperature and volume. When pressure is constant, the higher the temperature is, the larger the area of gas will become. Let's make our balloon a hot air balloon. When we raise the temperature inside the balloon gets larger.
We can take these two gas laws and combine them with a third gas law called the Guy-Lussac's law. Guy-Lussac's law describes how gases act when heated and the relationship with pressure. Let's take our hot air balloon and make sure that it doesn't get any bigger. If we increase the temperature inside of the hot air balloon, the pressure will increase because the molecules begin moving faster and faster. If we take this gas law and combine it with the first two, we can make a Voltron-style combined gas law. This combined gas law describes the relationship between temperature, volume, and pressure, and is a great way of modeling how gases behave in closed containers, like balloons.
But wind doesn't take place in a container. You could view the atmosphere as one big container, but it's just too big. With this, a lot of the gas laws don't fully apply. Some of the basics still hold though. As you increase the temperature, volume increases. However, heating a pocket of air won't keep it the same size in the expanse of the atmosphere. This concept can be confusing. To help illustrate this, we have a series of examples.
Let's say we have this wonderful landscape. If the sun heats up the land over here more than the other areas, the land will transmit some of its heat up into the air above it. Since the air is warming up, we can use a combined gas law to predict what happens next.
When the air gets warmer, it both expands and decreases in pressure. Since its pressure is less than its surrounding air, it is less dense than that surrounding air. You may have heard the phrase, heat rises. Like oil on top of water, the less dense warm air rises above the dense and cooler air surrounding it.
Let's say that over here is much colder than the area we talked about earlier. These colder areas usually form closer to the poles, like the Arctic or Antarctica. This is a result of the sun hitting the Earth at different angles. The air of this colder area is dense because according to the combined gas law, the lower the temperature, the higher the pressure as a result of lower volume.
Let's look at the situation so far. We have an area of higher pressure, our cold region, and an area of lower pressure, our warm region. Imagine a long balloon, like the one used to make balloon animals. If someone squeezes one end of the balloon, the other end gets bigger. You can also imagine a large airbag, where someone jumps on one side of it to fling someone else high into the air. In both of these situations, when you increase the pressure of one area of the air, the other air has to go somewhere.
In our landscape, This means that the dense air flows across the surface to the place where the warm air rose up and fills its place. High in the atmosphere, the warm pocket of air slowly cools down as it drifts over time, before sinking back down to the surface in that colder region. Then, it gets denser and flows its way back across the surface to be heated up again in the warm region. To a person standing between the warm region and the cold region, this flow of air is felt as wind.
So whenever you feel the wind blowing, you know that it's air traveling from an area of high pressure to an area of low pressure, as long as there are no buildings or mountains who divert the flow.
Learning how wind works is great and all, but how can we use wind? One way we can use wind is to generate electricity. By placing big turbines in the ocean or on land, we can use wind to spin a generator inside them, which produces electricity.
By choosing the right kind of wind turbine, we can help cut down on fossil fuel emissions and help create jobs for people who need work. The two turbines we're going to consider are the V90 3.0 megawatt onshore wind turbine and the V80 2.0 offshore wind turbine. V90 describes the size of the turbine itself, 3.0 megawatts describes how much power the wind turbine produces at peak efficiency, and onshore or offshore describes the turbine's location, either on the land or on a pylon out at sea. Out of these two, the V80 is best for the environment, while the V90 is best for creating jobs and helping the economy in general, and this is based on a whole array of measures.
So now you've learned that wind is the movement of air from a higher area of pressure to a lower area of pressure.
We learned that the combined gas law is what we use to determine the relationship between volume, pressure, and temperature.
And finally, you learned how wind has both the potential to create, as in generating electricity and economic growth, and it has the potential to destroy, like in deadly storms such as the 2020 Iowa derecho. Thank you for watching, and I hope you enjoyed.